Okay, guys, we are on section 7.4, the central limit theorem for proportions. In a population, the proportion who have a certain characteristic is called the population proportion. In a simple random sample of n individuals, let x be the number in the sample who have the characteristic. The sample proportion is p hat equals x over n. The population proportion is denoted by P, and the sample proportion is denoted by P hat. That little rooftop on there, we actually say P hat. If several samples are drawn from a population, they are likely to have different values for P hat because the value of P hat varies each time a sample is drawn. P hat is a random variable and it has a probability distribution. The probability distribution of P hat is called the sampling distribution of P hat. And we talked about some of that in section 7.3. You even had some homework questions with those definitions. Let P hat be the sample proportion of a simple random sample of size n drawn from a population with a population proportion P. The mean and standard deviation of the sampling distribution of P hat are as follows. The mean of P hat equals P, so this is very similar to last time when we looked at the mean of the sample distribution was equal to the mean of the population. Okay, so the mean of P hat equals P. The standard deviation of P hat, however, is going to be the square root of P times 1 minus P divided by N. So let's look at example 1. Example 1, part A, says find the mean of P hat and standard deviation of P hat if n equals 20 and P equals 0.82. Okay, so the mean of P hat, of course, equals P. So that's just going to be 0.82. Okay, then we have our formula for the standard deviation of P hat is going to equal the square root of P times 1 minus P all over N. Okay, and we, of course, know that P, we'll write that over here, is 0.82. And it tells me that N here is 20, okay? So I'm going to plug that in. I've got the square root of 0.82 times 1 minus 0.82 all over N, which is 20. We, of course, are going to need to put that in the calculator. Let's see if I can find one here for us. There we go. So I'm going to have a square root of, I'm going to use parentheses, 0.82, parentheses 1 minus 0.82, close parentheses, divided by 20. And that does give me 0.08591 approximately. So I have 0.08591. Okay. Part B of example 1 says find the mean of P hat and the standard deviation of P hat if N equals 217 and P equals 0.455. So I have P equals 0.455. I have N equals 217. I know that the mean of P hat is going to equal P. So that's going to equal 0.455. I know that the standard deviation of P hat is going to equal the square root of P times 1 minus P over N, which is going to give me the square root of 0.455 times 1 minus 0.455 all over n, which is 217. If I put that into the calculator, that's going to give me square root of parentheses. Guys, you can do a stacked fraction here if you want to. If I go to math and over to frac and I do n over d, okay, numerator over denominator, and I'm going to plug in 0.455 parentheses 1 minus 0.455 close parentheses all over 217. Okay, and that should give me 0.0338. 0.0338, and that is the second part of part B. Okay. We, of course, have a central limit theorem for proportions. It says let p hat be the sample proportion for a sample size of n and population proportion p. If n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, then the distribution of p hat is approximately normal with mean and standard deviation equal to the following, okay? So here's the deal, guys. Last time we had to have what? That sample size had to be greater than 30. Now, it couldn't be equal to 30, greater than equal to 30. It had to be greater than 30. You even had a homework question like that where it asks you if it could be seen as normal, and it told you that the number of draws was 30. The sample size was 30, so you had to say no on there. So in this particular one, when we are talking about p hat and the sample proportion, when we're talking about the proportion here, you have to say n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. Okay, so we will have to check that first. So that goes into the procedures for computing probabilities with the central limit theorem. Notice you see where it says we do have to check those to start with. Make sure they're both met so that it's appropriate to use the normal curve. Okay, that's what we did that for. That's what we did that for in 7.3 also. So let's look at example 2. Once we prove that we can use that, the normal curve, then of course we're going to use normal CDF. That's what that means. In order to use normal CDF, those particular things have to be met. Okay, example 2 says the general Social Security reported that 56% of American adults saw a doctor for an illness during the past year. A sample of 65 adults is drawn. A, what is the probability that more than 60% of them saw a doctor? Okay, so we need to identify a few things first. Okay, so what is that 56%? That 56% is actually P, okay? Because that is going to be my population proportion right there, okay? Then I have N equals 65 adults are drawn. Now 56% does need to be expressed as a decimal, so that is 0.56. The first thing we need to check is N times P greater than or equal to 10? And is N times 1 minus P greater than or equal to 10? Those are the first couple of things we need to try. So I've got 65 times 0.56, and we're checking to see if that's greater than or equal to 10. So when I put in 65 times 0.56, I do get 36.4, which is greater than or equal to 10. So that one checks. Okay, so let's do the next one. So that's 65 times 1 minus 0.56. Is it going to be greater than or equal to 10? Well, that is 65 times 1 minus 0.56 should give me what? 0.44, 0.44. Okay, and we're checking to see if that's greater than or equal to 10. And that should give me 28.6. And that is greater than or equal to 10. So they both check out. Okay, so I can proceed. I've got, I need the average of P hat, or the mean of P hat, excuse me. I know that equals P, and that is going to be 0.56. Then I need that standard deviation of P hat, which I know equals the square root of P times 1 minus P all over N, which is going to give me the square root of 0.56 times 1 minus 0.56 all over 65. So if I go here and I plug that into my calculator, I have, and once again, I'm going to use, I'm going to go to math, and I'm going to go over to frac and 1, and I'm going to stack that. So I've got 0.56 parentheses 1 minus 0.56 all over 65, and that should give me 0.0616, about 156, 157. Okay, so that's going to give me 0.06157. Okay, now I'm ready to do my normal CDF. It says, what is the probability that more than 60%? Okay, so in my normal CDF, since it's more than 60%, that means my lower limit is that 60%. So that's 0.60. Remember, we got to use a decimal. Then my upper, because it's more than, my upper is going to be 1E99. And then my average, of course, comes next, which is 0.56. My mean, I'm sorry, I keep saying average. And then my standard deviation is 0.06157. Okay, so when I put that into my calculator, I'm going to go to second bars. I'm going to go to number 2, my normal CDF. My lower limit is 0.60. My upper limit is 1 second, comma, 99. Then my mean is 0.56, my mu. And my sigma, or my standard deviation, is 0.06157. I'm ready. And that does give me 0.2580. Because if I round that 5 tells me that 9 has to round up, and that's 79 at the end, so that becomes 80. So I do get 0.2580 as my probability that more than 60% of them saw a doctor. B, we go back to our unusual question, okay? Would it be unusual if more than 70% of them saw a doctor. Remember, we're looking for if it's less than 5% or 0.05. Right now, we've got more than 60% is about 26% saw a doctor. So at 70%, we're not sure. So let's try it out. So I'm going to do a normal CDF again. This time my lower limit is going to be that 70%. So 0.70, my upper limit is 1E99 again. We've already calculated our mean, which we know is 0.56, and our standard deviation, which is 0.06157. So all we have to do is change our information there. And this one is pretty easy because I can just highlight that and hit enter. And then I go back and I can change that 60% to actually 70% and above. Okay, and hit enter, and I get 0.01149, 0.0115, right? If I do 4 decimal places, 0.0115, because it's 49. Guys, that's about 1%. Only about 1%. You're only about 1% actually, where we have 70% or more saw the doctor. Okay, so when you pull that sample, you only have a 1% chance of getting 70% of that sample that saw a doctor, that more than 70% of them saw a doctor that year. Okay, so is this going to be unusual? Yes, and that is because this is, well, we won't say this, we'll actually say the number. Yes, because 0.0115 is less than 0.05. And if you need to, just tell yourself this is about 1.15%, and that is less than 5%. Okay? If you need to think of it that way. All right, and finally, this is actually still part of example 2. We only have 2 examples here, and this is the second part. I called it number 2, but it says for a certain type of computer chip, whoops, I might need to spell that correctly. For a certain type of computer chip, the proportion of chips that are defective is 0.10. A computer manufacturer receives a shipment of 200 chips. Okay. A says, what is the probability that the proportion of defective chips in the shipment is between 0.08 and 0.15. Okay? So the first thing I need to do is I need to pick out a few things here. We need to pick out what N is. We need to pick out what P is. Okay, well, N is going to be 200 because we received a shipment of 200 chips. So we're looking at those in particular. That's our sample. And it says the proportion that are defective is 0.10. Okay, so that's my P. That's the proportion of the population that are defective. Okay, so that's actually about 10%. That's kind of high. So we need to find the mean of the sample, and we know that's going to be P, which is 0.10. And then now we need to find the standard deviation of P hat, which is going to equal the square root of P times 1 minus P all over N. Okay, well, that's going to equal the square root of 0.10 times 1 minus 0.10 all over N, which is 200. And if we put that into the calculator, we will see that we get a standard deviation for our P hat of 0.0212. I need to write that a little better. Okay. We do need to check and make sure that N times P is greater than or equal to 10. Okay. And we need to check that N times 1 minus P is greater than or equal to 10. So let's do our check here. N times P is supposed to be greater than or equal to 10. So I've got 200, that's my N, times my P is 0.10. I need it to be greater than or equal to 10. And it's going to be, because that's going to give me 20 is greater than or equal to 10. So that one checks out. If I try my other one, I'm going to have N times 1 minus P is supposed to be greater than or equal to 10. So N is 200. Then I have 1 minus 0.10 is supposed to be greater than or equal to 10. So I have 200 times 0.9 is supposed to be greater than or equal to 10. And sure enough, this is 180 is greater than or equal to 10. So we can use the normal curve to find my answer here. So I can say normal CDF, okay? And I'm looking for what proportion is between pretty much 8% and 15%, 0.08 and 0.15. So my lower is 0.08. My upper is 0.15. Whoops, sorry. My mean is 0.10, and that standard deviation is 0.0212. Okay, so I go over here to my calculator, and I'm going to clear that, second bars 2. My lower is going to be 0.08. My upper is going to be 0.15. My mean is 0.1. And my standard deviation is 0.0212. Okay, that will give me 0.8180. Okay, so that's telling me that's about 82% of the population falls in between that batch of being 8% and 15% defective is what that's saying. Okay, guys. B says, of course, we have another unusual. It's asking you if this is unusual. Would it be unusual for the proportion of defective chips to be less than 0.075, so less than 8%? is pretty much what it's asking for. So I want my normal CDF, and my lower limit is going to be 1e, negative 1e99. So I'm coming from that way far to the left, and all the way up to 0.075. My mean is 0.1 again, and then I'm at, my standard deviation is 0.0212. Okay, so I'm going to go over here, second bars, number 2. My lower is -1, second E, 99, comma, oh, no comma, sorry guys. Then my upper is 0.075. My average is 0.1. My standard deviation is 0.0212. And that gives me 0.1191. So that means it is not unusual because it is greater than 0.05 or it's greater than 5%. So not unusual. And that wraps up 7.4, guys.